And we're back. Greetings, Earthlings, and thank you for patiently waiting. I've just recently moved to a new apartment, so it's been a while with the relocating and stuff, so again, thank you guys so much. Hopefully, I'll be resuming videos a little more frequently in the coming weeks. Alright, so we left off with triangles, parallelograms, trapezoids, so there's going to be two parts to this video. The first part will be corrections to the triangle/parallelogram video, and the second part will be new stuff where we go over how to find the area of a tilted triangle, polygon, and curves and stuff like that on a coordinate grid. So first of all, some very quick corrections. I mentioned in video number 120, I said the word flip at least once or twice, and that should have been rotated 180 degrees. So to flip, at least my understanding of flipping is you go like this and then you flip it like that. What I intended to do, what I wanted to indicate is that you're going like this. So that's different. So that's a quick correction. Next, as was pointed out to me, I referred to the Cavalieri principle when we were trying to find the area of a parallelogram, and I talked about splitting it up into a lot of little areas. So like these little blue corresponding things, as long as they have the same base and the same height, these would have the same areas. And if you sum a lot of the same stuff, it'll be the same here and here. Except that's not what it's really about. So the principle actually refers to not little areas, but actual segments for our purposes. So forget this little area thing that I did, and instead just think of it if segment by segment, if you just look like this segment is the same as that, this segment is the same as the lower one, and so forth all the way down, then all together they'll have the same combined area. Now, using stuff that you guys probably haven't learned, using some ideas from calculus, these are actually not too different. If you shrink these little pieces enough, they become almost like little segments. So I don't want to make a big fuss about it, but just in case you see it somewhere else, these should have been little one-dimensional segments and not two-dimensional areas. Alright, so that's number two. Number three is a much kind of trickier and more fundamental thing that I really want to go over. So let me erase this. Alright, so in the parallelogram proof for the tricky case, I went over, and let me magnify this for you guys. I had something like that, and I said, well, you can't quite do the same reasoning you're normally taught in school, because if you just chop this, it doesn't go all the way down. So you have to do this in a few steps. So for example, we could chop it like this, then move this over so it's like that, and then chop it again and put that piece in there. And then we would get this nice box. However, I fell into a vicious trap, and I hope you guys don't fall into this. And what is this trap? I drew a very particular diagram. So in the diagram that I drew, it just so happens that this height looks to be about half of the entire height. So if that's the case, only then are you able to do this in 3 steps like this. So let's take the real rigorous, like the real general case where we're not going to be as lucky, and see what happens then. So that's going to be this skinny little diagram. So let's say we have something that's like that. Then when we try to chop it, this is going to take way more than just 3 pieces. So if we scoot this over, we might have to chop this again. So basically we're going to have to chop this a lot of times. We chop that piece. The point, and I'm not going to complete this proof, so that will be a more rigorous argument. If we keep doing this, we may have to do this a lot more. So like how many times? That would have to do with the ratio of this dimension to the entire height. But hopefully you can convince yourselves that eventually we start stacking this entire box, and then at the very last step we can get a nice fully formed rectangle. So that's the actual argument and not the nice case that I mentioned. Alright, with that out of the way, let's get to today's question. So let's say you're given, whoa, the world's falling down. Let's say we have a coordinate grid and you're given a triangle. So if we're given a triangle like this, let's say this is 1, 1, so this will be our x-axis, that'll be our y-axis, so this is 1, that's 1, maybe this is 1, 3 or something, and this will be 5, 1. So how do we find the area of this triangle? And this is not going to be our tricky case, that's just making sure we have some basics out of the way. So what are we going to do here? We're going to use these coordinates to find the distances. So since these are both at an x of 1, we're going to look at the y's. So the y's go from 1 to 3. So this would be a distance of 2. And then the x's, the y's here are fixed of 1 and 1, but the x's go from 1 to 5. So from 1 to 5 is a distance of 4. So how do we find the area of this triangle? We would take 1/2 of 2 times 4 and we'd be done. All right, that's not what I wanted to go over with you guys. Let's say we have a tilted triangle. So our triangle might be something like that. Now, I'm not even going to give you numbers. You can assume we have, well, let me put some coordinates on here. 1, 1. This could be 2, 4 or something. And this might be, I don't know, 5, 3.5 or something. All right, so we're given coordinates for each of these points. And now the question is, find the area of that triangle. So there are going to be 3 ways that at least I know of to do this, and maybe more. So the traditional way, well, let's back up a second. How might you guys try to do this? You might ask yourself, what is the base? What is the height? Well, we haven't covered this, but we're going to cover the Pythagorean theorem in a few videos. And what that's going to allow you to do is find the distance from any 2 points. So for example, let's say we find this is a distance of 5 or whatever. We could find the length of any of these segments. Even so, let's say this is our base. We need to find this height. And because this is tilted, it's a royal pain in the butt, right? So ideally, notice in the previous triangle, it was nice and aligned with our x and y grid. So even if it's not a right triangle, like even if the triangle is like this, as long as one of the sides is perfectly parallel to one of your axes, it's going to be very easy. So there are the 3 ways that we're going to learn how to do this, or that I want to kind of point out. The traditional way is to use the Pythagorean theorem to find some of these distances. So let's say we could find the length of the base because we know these points. But then you'd have to use some equations of lines to find this height. We're going to learn how to do that in a few videos, but for now, let's just say that's going to be way too annoying, and if you're lucky, that'll take you 3 to 5 minutes. If you're like, I couldn't probably do that faster than 3 minutes myself. So let's just say 5 minutes, 5, 10 minutes, whatever. That's a very tedious procedure. So let's see if we can do something a bit more creative. Also, aside from that whole linear line equation approach and Pythagorean theorem, which again, we're going to learn how to do that later, there is another way we could do this, which is more of a kind of like a fun curiosity, but not really critical for our needs. So I'll just write it in case you want to read about it, and that's using Heron's formula. Now, for that, you would still need the Pythagorean theorem. So using the Pythagorean theorem, you could find this distance, that distance, and that distance. And what this cool formula allows you to do is to basically throw in to your blender all of these numbers, and out pops your area. So, and if there's a ton of requests to go into that, we might do that, but I don't feel that's part of like the core stuff I want to cover right now. So that would be method number 2. So again, recap. Method number 1 is this tedious Pythagorean theorem plus equations of lines to find this tilted height. Method number 2 is Pythagorean theorem and Heron's formula. And method number 3 is what I want to go over, which is the nice way to do it. So, let's back up a little bit. in the area of a triangle, we talked about the box technique. Now, the larger principle here is the idea of a hammer. So, what's a hammer? So, in the triangle case, we first proved the right triangle area, and then we used that to prove the acute triangle and the obtuse triangle case. So, in other words, this simple case served as our hammer. So, we first build our hammer on a simple case, and then we use our hammer to crush harder and harder problems. That's going to be a really big theme. And if you guys are wondering how do you do some of these more challenging things, just think about, can you build a hammer in a simple case? Use something nice and leverage it. All right. So we are going to use something very simple, which is the box technique. Doing this directly, we said we'd need to know the base and the height, and that's pretty tricky. So let's put it in a box. So I'm going to make this blue. Here we go. So we're going to put it in a box. Now, the original approach of trying to find the base and the height, that's a forward approach because it's saying like I want to attack the problem directly. The box approach here is we're going to attack the problem backwards. So we're going to say, let's put this in a box. Now, what's special about this box? This box is aligned with our x and y axes, and remember we said anything that's parallel or 90 degrees to our axes is very good for us. So the box is very easy. We could find the whole box. So for example, this goes from 1 to 5, so the box would be 4 on the width, and it goes from 1 to 4, so it's a 3 by 4 box. So how do I get the 3? It's this coordinate of 1 and this coordinate of 4 minus 1. So what are we going to do after that? Well, we have our entire box. We are going to subtract these 3 triangles. Now, that may look like a lot of work, but remember, each of those is very easy because each of these are going to be 90-degree angles. So these are 3 right triangles. So I'll just do one of them so you guys can see how you would do this. So let's take this upper right one. So we're going from a coordinate of, the x coordinate here is 2, and we're going to 5. So this would be 3 that way. And since this is 3.5 and we're going to 4, this would be 0.5. So if you want to find the area of that triangle, you do 1/2 of 3 times 0.5. And in this manner, you would subtract each one of these 3 from the entire rectangle, and by working backwards, you'd find that triangle. All right, so hopefully you guys enjoyed that. That's how you find the area of a tilted triangle on a coordinate grid. But wait, there's more. You might think, oh, well, these are like little baby shapes. You can't do anything really fun or interesting or powerful with this. So let's take some wacky polygon. Let's say we have a shape like that. So this is a pentagon. It need not be a regular pentagon. It could be all sorts of weird shapes. But here's the idea. We're going to put it in a box. So make sure you draw the right size box. There we go. Now I'm not going to crunch all the numbers, but let's see what we'd have to do. So here we have a triangle, so that's nice. Triangle. We'll deal with that in a second. Triangle. And this looks weird, so we're going to have to split that into 2 non-weird shapes. So why don't we do this? Make a little rectangle here, 2 triangles. So there you go. So by working backwards, you can find the area of any polygon in 2D on a coordinate grid. So this is a very, very powerful technique. All right, now this is kind of like a bonus thing. This is the main thing I want to show you guys, but I want to show you guys that you've probably heard of, some of you, many of you have heard of calculus and curves, but don't be scared about it. It's nothing really crazy. So let's just see how we could take this idea further. We're not going to actually go too far into it, but I'll just give you guys a taste. So what's harder than polygons or things that are, many-sided? Things that aren't even, quote, sided, things that are smooth or curvy. So let's say we have something like that, and I want to find the area of this weird thing. Now, I might have an equation, hopefully, for that curve, but it can be really complicated. So again, let's try to put this in a box, except we're not going to put it in one box, we're going to put it in many boxes. So let's say we take a box like this. So I think you guys have the idea. I'm not going to get too far into it. If you chop it up into a lot of rectangles, you can approximate the real value. Now you might think, well, I don't want to approximate, I want the exact value. And that's what calculus allows you to do. So what all calculus is going to be saying, let's take these rectangles and make them a lot thinner and a lot smaller, because that way we won't have these huge errors over here. So we don't want all these errors, right? So the smaller you make them, you'll see that the error goes down and down, and in the infinite limit, basically, you'll have no error. So that's all calculus is. You're trying to calculate something really complicated in terms of something really simple. So again, we're using a hammer. Very powerful idea. All right, I'll see you guys in the next video. And also, for those of you that really want to go down a rabbit hole, I'll put a link in the description to this bonus thing on Professor Tadashi's lecture on deformation, where again he uses a simple concept to crush a very hard problem. All right, see you guys in the next video.